Okay, so in this lesson, we're going to be taking a look at some atomic structure beyond just the history of the atomic model, because at this point you know about the modern model of the atom, or the wave mechanical model. So so we're in the model that we still use today, and it's time to start learning some details about the atom. We are definitely going to focus on the periodic table today. You probably don't have a copy of the periodic table yet, but what you could do is you could quickly Google a periodic copy of the periodic table, so you have something to look at and answer some of these questions on your own. We're going to take a look at subatomic particles and their charges, their masses, and we'll even figure out how to calculate the number of subatomic particles in an atom. It shouldn't be too hard. So, homework, none to speak of, announcements, ask me in class if there is anything. As for these do now questions, you can take a moment right now, you can pause the video and you can write down these do now questions, put them in the classwork section of your binder, because we will answer these do now questions in class when I see you guys. So yeah, pause and write these down. Okay, so once you Google your reference table, if you look up the New York State reference tables for Regents chemistry, and scroll, maybe 2/3 of the way through the reference table that you find, you'll find this periodic table. This is the one that you'll be given by New York State on the day of the Regents, and that you'll be able to have with you all year long when you're in my class. So just make an effort right now. Try to find this one so you can have it and save it to your device so you'll always have it. And we'll use it throughout class today. So let me go ahead and go through some of these organizing slides. So subatomic particles and charge. First of all, the word subatomic. Subatomic means smaller than an atom. So it definitely is going to be referring to the smaller parts that an atom has. When we first started learning in this class about subatomic particles, it was in the context of Thomson. Thomson, who had the cathode ray tube and was able to develop the plum pudding model. He was the first person to describe subatomic particles, and the one that he discovered was, in fact, the electron. And he also posited that there was another particle called a proton, which would neutralize the negative charge on an electron, but the proton wasn't really discovered, quote unquote, until Rutherford, because Rutherford was able to show that the nucleus had a positive charge by doing his gold foil experiment. All right, so subatomic means smaller than an atom, and the charge of each of those particles is relatively easy to remember. Proton has a positive charge. In my opinion, it's almost built into the name itself. Proton just sounds positive to me. Neutron has a neutral charge. It doesn't have a charge. I usually write a 0 for that. An electron, most of us are already aware, electrons have a negative charge. So if I'm thinking about which subatomic particle might repel each of the following, I need to be thinking about charges, and I need to be thinking about the fact that opposite charges attract, and the same charge would repel. So if I want to repel a proton, I'm going to need to use another proton. If I want to repel an electron, guess what? I need to use an electron to repel it. But if I want to repel a neutron, that's a trick question. I can't repel a neutron. Just to help us organize these charges, let's place each subatomic particle on the number line by charge. Pause the video and think about where you would place each of the 3 subatomic particles we've discussed so far on this number line. And when you come back, I'll have the answers written. Okay, so I used some interesting symbols here. E- is the symbol that I'll use a lot to represent electron. P+ is a symbol I use to represent proton, and N0 is a symbol I use to represent neutron. Okay, so we have to have a unit that represents the mass of a subatomic particle. And some people would use kilograms for this unit, but in chemistry we found that it was really convenient not to use kilograms, and the reason is because these atoms are so small, and a kilogram is really big compared to an atom. So we were ending up using these really small numbers of kilograms to describe the mass. So what a lot of chemists do is they made up their own unit and for measuring the mass of an atom, and that unit is called the atomic mass unit. An abbreviation that we use for atomic mass unit often is just the AMU, and it's really simple to use. We can use it to describe the mass of a proton. For instance, the mass of a proton is 1 AMU, and the mass of a neutron is also 1 AMU. The only difference between these two particles, the proton and the neutron, is their charges. The proton, you might remember, has a positive charge and the neutron has a neutral charge. Now, electrons have a reported mass of something like 1 over 1836 AMU. It's really, really small. But actually, on the regions, typically we don't do that anymore. Almost always on the regions, we say that the mass of an electron is 0 AMU. This is a reference to the model that you guys just learned about the modern model of the atom and how the electron it's more than just a particle. You can think of it as energy or as a wave. And energy, of course, doesn't have mass. That's what distinguishes it from matter. And so we would just say it has 0 AMU. Otherwise, it's extremely small, which is also referencing the fact that electrons are partially particles, but also partially waves. So, of the two subatomic particles that move around the least, it's definitely reasonable to assume that the subatomic particles that move around the least are going to be protons and neutrons. And there's a couple of ways to think about that. For instance, both the protons and the neutrons are stuck inside the nucleus. That's where their location is. We actually give them a special name. We call protons and neutrons nucleons. Nucleons are particles that are stuck inside the nucleus. That's their location. And so being stuck inside the nucleus, they're not going to move around much at all. And in order of decreasing mass, if I just wanted to order these things, the heaviest of all is a neutron at just about 1 AMU. It's actually just a little bit heavier than that. You don't need to know that first, really it's a detail. Protons are also 1 AMU, so you could think of protons and neutrons as being tied, and you wouldn't miss any points on the regents. But protons actually are just a fraction lighter than a neutron, and then a very distant third place is electron, which is going to be by far the lightest of the particles. So when we calculate the number of subatomic particles in an atom, you can use your periodic table to give you a lot of that information. So when you want to figure out how many protons an atom has, really you just need to go to the periodic table, and there's a number in bold beside the element that will tell you how many protons it has. For instance, you can reference your periodic table for this now, but definitely look up hydrogen, definitely look up carbon, and let's say definitely look up lithium. Those are all towards the beginning. And hydrogen, you'll see a big bold 1 beside it. Carbon, you should see a big bold 6. And lithium, you should see a big bold 3. So just make sure that you find those on whatever periodic table you've pulled up. And that is the number of protons that each of the atom has. So lithium has 3 protons, carbon has 6, and hydrogen has 1. So just look on your periodic table to find these numbers. This is always true for the atom because all atoms of a given element have the same number of protons. So all atoms have the same number of protons, therefore it's always true. How can you figure out how many electrons a neutral atom has? This is a different question. So electrons are not, you're not going to see just one number that has the number of electrons an atom has. If you're looking at the periodic table that New York State gives you, it's going to give you several numbers for the electron configuration. So for instance, if you had already looked up carbon and it had a big bold 6 for the number of protons, you may have also seen a couple of numbers that would have said 2, 4 also in that box for carbon. Lithium, you maybe would have seen 2, 1. And for hydrogen, you would have just seen a 1. So those numbers that I just wrote in and circled, those are called electron configurations, and you can add the numbers up to figure out how many electrons it has. So for instance, hydrogen is just 1, 2 and 4 is going to add up to 6, so that's going to be how many electrons carbon has, and 2 and 1 add up to 3, and that's how many electrons lithium has. Now, if you're a person who likes patterns, you probably just realized a very easy shortcut, which is that in a neutral atom, the number of electrons it has is equal to the number of protons. So I'm going to write that in. It's going to be equal to the number of protons. And so you can just look up the atomic number or the number of protons. That's the big bold number, these guys. And if an atom's neutral, then that's also the number of electrons that it has. So this is always true, basically because protons are positive 1 charge and electrons are negative 1 charge. Therefore, if the atom is neutral, then they're going to be equal protons and electrons. Okay, so I want you to copy down these pair-up questions for tomorrow. The table should not be hard to copy down. And the questions themselves, you should be able to copy down without too much trouble. But these are all answer choices, so you shouldn't feel the need to have to copy these down. But you could copy down this question, that question, this question, and that one. And then also with summary here, you could copy it down, but we will go over it in class tomorrow. Thank you, and have a great rest of your weekend. Bring your Cornell notes tomorrow.